Welcome again to the NPTEL course on storage systems. In the previous class, we looked at certain concepts regarding performance of storage systems. So, another aspect of storage is security. We will briefly look at it to get some idea about the kind of issues in security. Now, one thing you should notice is that storage is a critical aspect of a system. Without storage, you are like a person who has no memory. You can't boot a system, etc. Okay? So, it is basically a critical piece of data without which nothing is possible. Okay? So, if storage is to be a bedrock, okay, on which rest of it all stands, you have to make sure it is highly available. What does it mean highly available? In spite of various problems, it should still be accessible. For example, should be resilient to failures. Nowadays, there is this what is called distributed denial of service attacks or denial of service attacks. Somebody is trying to prevent you from doing any work. They are not luckily stealing your data or destroying your data or basically corrupting your data, but they are preventing access to your data. This is a fairly big problem, and so people, and actually now it is becoming attacks between nation states also. Certain countries are deciding to figure out how to get back at other countries without any blood. Okay, this basically do it through computers, right? So that also is going on. So you also, if you have storage, you might have to prevent it from malicious tampering, and this can happen inside and outside. You can have people inside your organization who can do it, people outside also can do it. And people generally say people inside are the more difficult enemy. Okay? Basically, most studies say that 70% of all tampering happens because of inside people, 30% from outside people. Okay? And you also want to control access, you want to avoid leakage of information. Certain things are sensitive. For example, if you know that there is somebody is building an airport, right, and it is leaked to the right people, they can buy the land near the airport and make a big killing, right. So some information is critical. If you take your job of governance very seriously, you should avoid giving inputs by which certain unscrupulous parties can get advantage. Okay. So same story, okay, and this can be in the form of speech or it can be in the form of files. Okay. And so it's up to you to figure out how to make sure these files are not in the wrong hands. It has to be released only at a particular time, not before that. Okay. So that's one. Other thing also is what is called prevent replay of stale information. Sometimes you are asking for some information and somebody maliciously giving you old information, so that you have a wrong information and do the wrong things. Okay. So this also can be quite dangerous. So that means that if some data has changed in spite of multiple copies anywhere, you have to ensure that the wrong information not sent to you. There are some situations where this is absolutely critical. There are some situations where it is not that critical. A good example is if you are watching cricket, if somebody gives you a score which is delayed by 2 minutes, it's not the current score, right? It doesn't matter that much. Okay, it's sort of a soft system. It doesn't really matter. But for some people, it's absolutely critical. Okay, it has to be accurate information. Okay, so that's why it's important for you to use correct protocols. We're not really gotten into protocols right now, but generally protocols are messages sent across two entities: storage devices or storage consumers, storage producers. Okay, and you have to make sure that these protocols are also safe or correct. Okay, so this turns out to be a non-trivial problem. Okay. And sometimes it turns out that you need what is called tamper-proof archival storage. How do you show that some storage has not been tampered with? Okay. A good example is if you have in a mobile phone, you have a, what is it called? You have a SIM card and it stores some information. Okay. And it has to be tamper-proof. Basically because you have the device in your hands, and if you are a very clever guy, if you can see enough of what is there inside, you can probably change it. The idea is that if you can change it, then it is not good for monitoring or tracking certain things, okay, which the government or other people might want to look into, okay, or some proprietary reasons. I don't want to get into why somebody wants to monitor you, but sometimes it is necessary, okay. So if somebody is, because the gadget is in your hands, you can be a physicist who knows how to send laser pulses, okay, which can modify the bit, okay. Who knows what sophistication you have? Nobody can tell you which person has got what sophistication, okay. Or it could be somebody or probably a criminal bent, and he is basically has a whole lab which does nothing on this. And there are people who can take a chip and take out one layer at a time, okay, and then see what the bits are inside, okay. People can do all these things, okay, because basically we are talking about few microns. You can get microscopes and whatever similar kind of devices which can look at microns, nothing very deep, okay. So you can look at it. So what is important is sometimes you need what is called tamper proof. Okay, you are a sophisticated guy, you can peel one layer at a time and figure out what the bits are. But the important thing is that the minute you remove it, right, somebody should be able to know that you have removed it. It's like the way in our country, for example, or many other countries, when you send a post, they have put a lac, they put some, what is it called, lac, right? You seal it with a lac, right, LAC, and if somebody has opened it, it comes off. It's a bit fragile stuff. The minute you open it, you can see that somebody has taken it off, right? It's not that that seal is not there, right? Therefore, you can figure out it's been tampered. Somebody in principle can do it. We need some such things even in the case of storage systems. Typically, you can do it by, what you can do is you can have some what is called, if you use computer cryptographic kind of models, you can have what are called hashes, and if you do certain things, then if you change some things, the hashes don't no longer match, and therefore you know something has happened, okay. So your tamper proof can be at multiple levels. It can be physical level, or it could be at the logicals or bit level, or at the cryptographic level, those kind of levels, okay. Again, if you look at security and storage, it's at many multiple levels. I'm just listing few of them at the file system level, at the block level, at the device level, okay. So the file system level means the file system takes care of encryption and decryption, for example, that's a possibility. Or it may not use encryption and decryption, it just makes sure that you can't look at my stuff, vice versa. How is that possible? By using what's called access control. It's not using cryptography. Cryptography is a mechanism, okay. So the question is whether you use that mechanism or some other mechanism. If you use cryptography, then use encryption, decryption, that's one way. You make the bits available, but the person can't read it. Or you can do what is called physical separation. I ensure that whatever happens, you can't look into my stuff by having, for example, access control, right. I lock certain things and keep it aside. It's not encryption, decryption, it is just physical, in some sense equivalent of physically you are separating it out, okay. So that also you can do. You can do it at the block level. For example, if you have a RAID device somebody makes, he will provide a block level interface, and he can assume the responsibility for encryption and decryption. Or the device level, for example, many disk vendors nowadays give you whole disk encryption. You can encrypt the disk and it is decrypted at as fast as a regular disk can, basically because they have chips which can do what's called online decryption, or forgotten the term. It's called I'm not able to remember the term, but basically it means that as you are writing it, it can encrypt, and as you are reading it out, it can decrypt at the same speed. You know, don't lose any speed in this, okay. So in addition to these things, if you are building very large storage systems, you are going to use networks to connect up multiple pieces of storage, or to keep replicas, you want to keep them, right. So in the storage network, you have every single aspect of network storage issues will also be here, okay. Just like the number of layers in a network are going to be also present in your storage stack, because you are going to have storage on top of the network, okay. Same here also. Typical security issues are integrity, secrecy, availability. Integrity means nobody should be able to modify something. Secrecy means somebody should not be able to see it if it is not appropriate for somebody to other than authorized parties to see it. Availability is figure out a way in which, in spite of people trying to prevent you from accessing information, still be able to survive. Okay, DOS attacks. Okay. Now there are other interesting issues also coming up with new devices. For example, flashware. What is the issue here? If I am trying to destroy some piece of information, I am unable to let us say get access to the normal route. What I will do is I will find a way in which you cannot use the device somehow. How can I do it? I just keep writing, preferably to the same location. I essentially burn the flash there, equivalent of that one. Okay. Essentially keep making sure that the device starts running out of space. This has to happen also in other contexts. For example, in the 1960s, we had something called core memory. The core memory was basically a magnetic kind of thing, and it would have two states 0 and 1, and it goes to some current is sent, it flips in one direction or other direction. Now somebody can write a small tight loop. Okay. Basically you branch to the same memory location and keep on executing it. That means the current is going through that coil all the time. Okay. And finally that particular coil element gets burnt out. Okay. Similarly in flash also, in spite of your wear leveling, you can somehow ensure that you are essentially basically you want to force the device to be unavailable. How do you make it unavailable? Normally in a flash kind of device, SSD kind of device, you have some spare space so that to handle this worn out things. The idea is to keep writing in such a way, just like the way you are doing in the core memory, right? You just keep on looping across a single word, right? You just only keep touching one particular area. Okay. Here also you can keep on touching in spite of wear leveling. You try to make sure that there are so many writes are done so that your spare capacity is completely gone and people finally have to write off the device. Okay. Somebody has to take it offline, copy it, etc. Essentially it's a DOS attack. Okay. So that also is possible. So there are now solutions even for this, that even if you try to write it, they see the kind of pattern that is being written and they try to take countermeasures for it. Okay. There are some people who are working on this kind of problems. Okay. The other aspect of security and storage is that you will find that the storage medium is often a good medium for spreading viruses, because you use that as a way to exchange information. So viruses often travel through this mechanism. You must be quite well aware of this problem. Okay. And what is the problem with this? It turns out that there are no foolproof way of checking if something is a virus. You can have a lot of false positives, right? And so theoretically it's impossible. There is no way to prove that something is a virus or something is not without false positives or false negatives. Okay, it's not possible. Okay. The other aspect of security and storage is that you can, as you mentioned before, you have this notion of metadata and data also. Metadata is small, data is large. Okay. So oftentimes you might have heard about something called public key encryption systems. There are two types, symmetric and asymmetric keys versus basically you have systems with two keys, public key encryption systems, but these public key encryption systems are extremely difficult for large amount of data. You can only use it for small amount of data. Okay. So solutions which depend on public key encryption models for data will not work, absolutely will not work, because it is just too large. Okay. Because essentially this involves public key encryption requires exponentiation, and that takes time. Okay. So typically, for example, if you can do, okay, I got the word, okay, wireline speeds. Okay, what I was trying to say at this was wireline speeds. Okay, typically you can do this symmetric encryption at what is called wireline speeds. That means as it is coming in, you can do it at the same speed. Okay, whereas public key is not possible. Okay, for example, you often get about few millisecond delays with public key encryption. Okay. So luckily it is not much bigger than the disk delays, so you can hide it. Basically it's in the noise, but still you can't really depend on it. Okay. It's just not a reasonable thing for large amount of data. Okay. So that's why you need what is called stream ciphers. with symmetric encryption data. Okay, so this is happening at wireline speeds. So our system actually has got both metadata and data. That means you have to oftentimes do both. Sometimes you might want to do public encryption only for metadata, or you will do stream ciphers for symmetric encryption for data, or sometimes you just use these symmetric encryption for everything. We will briefly look at DVD. DVD uses some type of encryption mechanism. We will just look at what they do there. Other aspect of security and storage is that when you collect a lot of data, you aggregate lots of types of information, and sometimes new patterns arise or new secrets leap out from the aggregated information. What is if information is kept separate, some patterns may not be visible or some secrets are not complete and not usable. But once you put them together, it turns out that you can start seeing something useful coming out of it. Okay, and so this is certainly a problem with network storage, because by definition storage actually aggregates a lot of information, right? So it's aggregation attacks become possible with large amounts of storage. Okay. So as I mentioned before, there are two types. Basically, you can do access control, or you can do cryptography. You can do, that's physical separation mechanisms or cryptographic mechanisms. Various kinds of mechanisms are possible. Okay. So what initially started out in the beginning was that we started with access control mechanisms. I think all of you are familiar with this notion of RWX at a file level. It tells you the user, the owner can read, write, or execute some files, whether if you are a member of a particular group, what group owners can do with that file, and if you are anybody outside this user or group, what they can do. Okay, there are three things out there, right? Also, this has this is what is called a discretionary access control mechanism. That means that if you get a permission to do something, you can in turn give it to somebody else. Sometimes this is not a good model. If some very valuable information is there, I give it to you, but I also want to control what you do with it. Okay, and that is what is called mandatory access control. That means that in spite of my giving you some piece of information, I still want to completely control what you do with that information. Okay. Typical file systems use DAC, okay, discretionary access control. For example, ext3, ext2, all those things have typically only DAC, discretionary access control. That is, I give you some file and you can do what you want to do with it. You can give it to a friend or anybody, but I don't have any control about what to do with it once I give you permission. Okay. And there are newer models in SC Linux, is a model available in Linux. There you can do mandatory access control. We will briefly talk about it later. Okay. So you have access control mechanisms. You can also use cryptography. Okay. I think we discussed it earlier. It turns out key management becomes very critical here. Without key management, cryptography is a very difficult thing. There is something called identity based encryption, which is a new research area that people are working on. That might solve this problem, but it is still not clear. Okay. So again, one thing you have to keep clear in mind is cryptography is a mechanism. Okay. Whereas security policies at a higher level. Okay. You decide who should share what. That is a policy decision. Whereas cryptography is a mechanism. It's one way to do something. So the policy can be the same, but it can be done in many different ways, and cryptography is one mechanism. So oftentimes people confuse cryptography with secrecy and other things. Okay, and that's why there's an interesting comment. Often, if you think that somehow you put this masala called cryptography into it, it solves a problem, right? That means you probably don't know what you're talking about. Okay, that's an interesting quote. If you think cryptography is the solution to a problem, then you don't know what the problem is. Okay, why is that? Because you have not really figured out how to do the key management. So many things are not specified. Just because it's a cryptography I'm going to solve, it's not going to solve it. And we will see it in the case of DVDs. Why the DVD system finally, it's a completely broken system. Okay, the DVD encryption system. Okay. Again, if you want to think in a slightly larger sense, worldwide information systems, network storage systems, etc., they require much more sophisticated models. Because in this kind of models, in this RWX, etc., right, we had users. But suppose I want to add what is called anonymous users. Does Unix allow anonymous users? It doesn't have the notion seriously. Okay. Okay. You also want to have the notion of delegation. I have, for example, many busy people have secretaries, right? I don't have the time to do it, I delegate it to somebody. Can I express this notion of delegation? Okay. Trust management, how many levels at which I can delegate it? Okay. I may want to delegate only to only 3-4 people, okay. I can't go beyond that, or it can be smaller. It has to be scalable, okay. That I think some of you might have come across situations where Google or Facebook seems to be very unresponsive, because they might be doing a lot of authentication, and somehow those servers there's some fault somewhere, and there's some overload somewhere, and it's not going through, okay. So you have to worry about scalability also, okay. And all these things are critical, because if you notice in our country also, you have something called, people are pushing something called unique identifiers, UIDs, right? And there also, if they are saying that they want to do for a lot of transactions, banking transactions, so that means that you have to now keep track of all this authentication, etc., for everybody as they are doing banking transactions, many of them, okay. If they want to do a real-time system, it turns out to be a very difficult proposition, because you have to have a highly available system which will work in spite of all the load that you can put on it, okay. It's not a trivial problem, okay. That's why you need highly available access control, okay. You also need information flow models, which is basically what I was talking about earlier. If you have this mandatory access control kind of models, I want to be able to say where things are, okay, where things are going, where the information is going, can I keep control over it, okay. A good example of this is, suppose I have a virus scanner. I am doing virus scanning on my machine, and this virus scanning program is I got from somewhere. It could be open source software, it could be from a company, but I can't figure out what its capabilities are. I am just a naive user, and now it is for virus scanning, it has to touch every single file, right. That means that a virus scanner can read every file in principle. It has to be able to, otherwise there is no way it can find if the virus is there. Now, what I am not clear is, can it be sending some of my data outside? How do I know it is not doing it? And notice that you can say possibly that, okay, I will cut off the network, okay, then it can't do any bad stuff. But you will notice that virus scanners are as good as how updated the database is. You buy a virus scanner and a new attack comes in, somebody will update that database of net viruses and whatnot. That means that your virus scanner should be able to update itself. If it is not able to update itself, it basically becomes worthless over a period of time. That means that by definition, your virus scanner should have ability to talk to network. But now I have a problem now. The minute I give it network access, that guy could actually be sending it wherever it wants, right. That means that I have to do something about making sure that the information I have in my hands, in the data that I have, somehow it has to be able to say that it can only do virus scanning but not send it out of the network, but it should be able to get updates from outside, okay. So something like that, you need to construct systems which have all these kind of capabilities, and for this there is a whole area called information flow models that people are looking into, okay. And even if you come up with these flow models, how do you know that whatever policies you have, okay, actually support the security policy you have in mind, okay. This is also another issue that comes up, okay. So just to make things a bit more clear or more realistic, let us take a look at one type of simple system, storage system, okay. All of us are familiar with CDs, DVD, probably not Blu-ray, but you must have heard of it, right. So CDs, when it was designed, when was it designed? It was designed in the late 1970s. Music CDs came out first in 1970s, late 1970s, okay. Before that, tapes were there, and tapes didn't have any protection, neither did CDs have, because computers were very rarely used in the 1970s, late 1970s, and PC was also not born. It was not a common available gadget, PC, okay. So this thing had no protection. Nowadays, if there is a protection on the CD, it is typically some password based some system, okay. There is some trivial system that is there which will ask you to log in something, okay. That means that it is executing some piece of code. That means it is somebody has mounted that CD, some program has taken control, it has complete control of that CD, and the program itself is asking some question and you have to log in, etc., or you have to give it some string which you cannot easily manufacture. It's basically like, for example, you are installing some typical Microsoft software in the olden days, right? It will ask you for a big string, right? You copy that string and then that guy will do some internal computation, hash it, do whatever, and say that, okay, this looks like a legitimate thing because I hashed it, it gave me some value which is what I am looking for, therefore it's okay. So it had those kind of mechanisms. When it comes to DVDs, they did something slightly more, they wanted to do something more systematic. But I am told actually that this DVD was probably sabotaged within this security for the system. Okay, somebody was in the committee which didn't want serious cryptography, or there is also some other claim that in those days when DVD security was decided, United States had a very restrictive policy on security of gadgets. Because they wanted to break into any system, the US government or the CIA, they have a specific requirement that you should be able to break into any system in those days. Okay, so the keys which are used for encryption and decryption had to be less than or equal to 40 bits. Okay, that is, it is widely believed that the US government had fast enough machines in those days that if you have a key of 2 to the 40 bits, they can essentially use brute force attacks to figure out what is there. Okay, so DVD was designed in those days. That's why we will see that your key cannot be bigger than 14 bits. Okay, so let's look at what these guys did. Okay, so now there are, what is the system with the DVD? You have a DVD players and you have DVDs, right? A DVD player is manufactured by some DVD player manufacturer, right? Not the media itself. I'm talking about a DVD player. Okay, it could be Sony, Panasonic, etc., right? So every DVD player equips a small set of player keys, possibly one or more per DVD player manufacturer. So Sony will have 3 or 4 keys. Okay, some other Panasonic will have some of few, etc., right? So every DVD player that you buy will have some set of player keys, okay, depending on who the manufacturer is. In addition, every disc, these are different from the DVD player manufacturers. This could be anybody else. Okay, it could be, for example, Hollywood or Bollywood or whatever, right? Whatever variety of people. Okay, every disc has a disc key, data block organized as follows. Okay, what do they have? There is a decryption key for that particular DVD, that movie or whatever. Okay, and what they do is they have a hash of it. There are hashing algorithms they use. They are not going to go into those details. So it's got a 5-byte hash of that disk key that is stored, and these things are stored in a particular place on the DVD, and there are some special restrictions, and the DVD players, they have to follow certain protocol to read it. It's not widely known. It is sort of what is called security by obscurity, because these DVD players are manufactured by some bunch of people. Amongst themselves only they know the secret, how to read it. Okay, same thing about this other things. Okay, the disk key is encrypted with various player keys. So there are so many manufacturers of DVD players. For every manufacturer, okay, they are going to have it encrypted, and that will be stored in these places. So what is the issue here? Every disk has got a hash, and you have the disk key, what is required to read the DVD, the movie, right? That is encrypted with the various player keys. The various manufacturers, for every manufacturer there is a corresponding encryption of that particular disk key required to read that movie, to see the movie. So these are the things. So you have it there. For some reason it is 409. So I suspect must be because of the limitations of fitting it into one sector. Okay, probably the size of this. Okay, so they also felt that probably there cannot be more than 409 manufacturers of DVD players worldwide, like whatever. Okay, so what do we have on a disk? You have a hash as well as the encrypted version of that disk key for various players. Okay, for various manufacturers, let's say. So when you present a new disk, okay, then the player knows which one it is. Okay, whether it is key 1 or key 10 or key 100 or whatever. Okay, it has a set of them, a few of them, 5, 6, I don't know, whatever. Okay, so what it does is it will attempt to decrypt contents the set of keys it possesses. It tries to decrypt. Okay, So, suppose for example, the player knows that it has a valid key for, because I told you there are so many slots 1 to 409. So, it has a valid key for slot 100 for example. Okay. So, it will basically decrypt it, use that, it will try to use the player keys, okay, and it will decrypt in slot 100, okay, because they are all encrypted here. So, out comes a possible key, okay, which can be used to decrypt the whole DVD contents, but does not know it because it is not clear, because there are so many players and so many DVDs, you do not know which one is which. Okay. So, if it, to verify that it is correct, you hash that same key that you got and see if it is the same as what you already have, okay, because there is a hash of it already. Hash of the key required to read the DVD is already present here. So, what we are doing is, you are basically taking the disk key that has been encrypted, you decrypt it with the player keys, okay, and then you decrypt and see if you get that actual disk key, and to ensure that that is the same as what you expected, you hash it again, see if it is the same as what you have earlier. If that is the case, then you know that the key is perfect, okay, you can use it, then you can decrypt it, okay. Now, the only problem here is that you notice this equation, this H is known and you just have to, you can generate all these KDs yourself, there is no requirement of any player key here. So, you generate, what if it is a 40-bit key, you have to generate 2 to the power of 40, okay. How much is 2 to the power of 40? It is about 4 gigabyte possibilities for 32-bit multiplied by 256. How much is that? So, you need to check about 4 into 256, okay, that is about 1000 giga, this is 1 trillion, okay, numbers of these things. That in those days was felt to be very huge, they decided it is not a problem, okay, or it was intentionally weakened for whatever reason, we do not know why. So, it turns out there are some additional things that they do, and you do not have to actually check 2 to the power of 40, there are some other let us say things wrong with the system. So, instead of 2 to the power of 40, it turns out you need only 2 to the power of 16. So, because it only requires 2 to the power of 16 possibilities, it turns out you can easily check it in those days even 450 megahertz per time in less than a minute. That is how it was decrypted, okay. So, okay, this is basically the one key. You want to actually see the contents of the DVD, there is something called the title key, you have to decrypt it with that KD you got, okay, and then they have some additional methods of making it even slightly making it difficult for you, but all of this failed finally, okay. What they did was, each sector of data files optionally encrypted by a key derived from this title key. As I told you, you had a disk key first and then you get a title key, and then you take the title key and XOR with some bytes from the unencrypted first 128 bytes of the each 2 to the power of 2k byte sector. So, there are 2k sectors in the DVD, you take the 128 bits, use that as input along with the KT, the key you got, use that as a way to feed it to what is called a stream cipher, okay. And this stream cipher is a symmetric key, therefore, it will give you, you encrypt, you can use the same string, or if you decrypt also you can get the same string, you get it back, okay. And this can be done fairly fast, okay. So, they chose simple enough techniques that they can do all this without any trouble, okay. But the basic problem was that in this part of it they made some big mistakes, I do not have the time to go into it, they make some big mistakes. So, basically instead of 2 to the power of 40 it turned out to be 2 to the power of 16 or something like that. That is the only number of possibilities that you have to check, and you will see that this kind of mistake also was done in Wi-Fi. I think you might have heard that in the, when in 2002 or 3 for example, there was some type of security which was totally broken, and anybody can actually access to your system very easily in those days, and later now you have a slightly better system now, okay. So, this DVD thing just failed, flopped in a serious way, and you might have heard of something called DCSS, okay. Some hackers who figured out the system, they released it, that is why you can read any DVD now, okay. It is not difficult, okay. Now, based on that particular problem, this Blu-ray people tried to avoid this problem, and they called it advanced access control system. But it turns out this problem was broken for a slightly different reason, which some of you must already know by now. Okay. Basically, whatever you do, however many levels of encryption you do, the keys needed to obtain unencrypted content is available somewhere in memory for playback. Finally, you are using some computer system, even if it's an embedded system, it's memory somewhere. Okay. That means that you write a simple device driver which scans the memory, kernel memory, and then tries it out. So you make sure that your embedded system is small enough, it's only got, let us say, not 1 terabyte of memory. Make it sure it has got the most, let us say 4 megabytes of memory, or okay, 16 megabytes of memory, or okay, make it 256 megabytes of memory. Okay, and everything you check. Okay, every single, I don't know, whatever. Okay, 40 bit or 64 bit, whatever. Okay, check it and see if you can decrypt it. Okay, so this is much smaller than the previous system. Okay, because here we wanted 2 to the power of 40, 1 trillion possibilities. Here, if you take a reasonable amount of memory and try to on that embedded system, nowadays you can open the embedded system and put your probes, oscilloscopes in this, and you can do all those things. You just need a determined guy, okay, who can look at it and see, and then see all the things and figure out which part of it is somewhere sitting in memory is the actual key that is being used for encrypting or decrypting. Okay, essentially you have to write a device driver. And what is the problem here? It's basically because it is your stuff is running on your device, and your device you can always open it up if you are clever enough, put the probes and figure it out. There are various people in this world who are good at this game. Okay, so we have done all this. Okay, so essentially the only way to solve this problem is by using what is called a trusted computing platform. What is that? Essentially, a trusted computing platform will only run trusted software, means those things that have been certified to be safe. For example, it cannot be a virus. I don't want a virus to be executing there, because a virus can be anything arbitrary, right? So a trusted computing platform will avoid allowing any software that doesn't match certain criteria, example being hash. Okay, for example, if you are running a compiler, it might have a hash. It will check whether that executable you have has a hash which is the same as what is to be allowed. If it is allowable, then it allows it, otherwise it won't do it. So any random virus will not, its hash will not match, so it will throw it out. Of course, this is very difficult to design and make it work. There are all kinds of attacks. Okay, just like your simple device driver attack, right, where you just can scan the memory. It turns out even if you build a trusted computing platform, there is some place, there is a bus somewhere, you know, computer architecture, there is some bus, etc. You can tap the bus and you can do various things. Okay, so it's a very difficult problem, and the best you can do is you can do all this stuff against the average user. All these things are quite fine. The minute you go against a skilled attacker, the guy can essentially get whatever he wants, essentially. Okay, the guy has to just spend the amount of time. Okay, so essentially it turns out that the PC is not a trusted computing platform. Okay, and nowadays there is some effort moving in that direction. There is something called trusted boot, you might have heard about. Windows 8 is coming with trusted boot. Okay, so because their Windows platform has been widely attacked through viruses and whatnot, malware for the last so many 20 years plus. So finally Windows 8 is going to have what's called a trusted boot, so that viruses cannot easily get in. Okay, that means that only those software, only those executables with a particular hash, right, will be allowed. That means that there is a chip inside which has tamper-proof storage. We discussed already tamper-proof storage. Basically, that kind of storage which is sitting in a chip, even if somebody scrapes it off and tries to look into it, it will destroy the information. That's how it is designed. It's called tamper-proof storage. So somebody will have tamper-proof storage at the chip level, and it will have some of the hashes that are to be allowed. And these hashes can be inserted or taken out, okay, by some specific mechanisms. Okay, so if you have that kind of a platform, then you can essentially avoid this kind of problems. But currently there are very few platforms which have this property, Windows 8 and newer generation devices might have this property. And typically mobiles also, if you want to do what is called mobile commerce, right? You want to, because it's finally again your mobile is in your hands. If you're a clever guy and the bank or organization is keeping information about your transactions in the mobile, let us say, then if you're a clever guy, you can go and change that thing, right? That means again you need to have what is called tamper proof storage or whatever protocols have to be there, so that when you modify something, somebody is alerted that yes, the guy has done something wrong, information is lost, but at least I can say that somebody has done something bad. Okay. So there are various attempts to get a trusted computing platform, but they have not yet. They are not yet widespread now, but probably in the next year or so it will start happening. Okay, because right now Windows 8 is coming. I don't know how successful it will be, but that one has got some trusted boot aspects. So that might have a trusted computing platform, in which case it may be. But generally, when all these systems were being designed, they could not provide this trusted computing platform. Therefore, I am told that Blu-ray also has been hacked. Okay. It also basically by using this device driver hack, okay, you can basically figure out what's going on. Okay, I think I'll just we already mentioned a bit, but let's just quickly look at some access control models. Okay, in a discretionary access control model, each subject decides how its objects interact with others. Security manager keeps access control matrix. Okay, it turns out there are theoretical problems here also. It turns out even in discretionary access model, checking what is called a safety problem. That is, I give certain privileges. Is it possible for some other person to get more privileges than what is allowed? Okay, what is called the confinement problem. Okay, it turns out even this is not decidable. Okay. Okay, so I think I want to. There's also something called mandatory access control model. The security server in every instance will decide how any object interacts. Okay, there's also something called a role-based access control model. That means that just like in Unix, you can be part of a role. You can be a system administrator, right? So the thing is here, you're not going by your user permissions, you're going by your roles. Depending on the role, you are allowed certain things. Okay, this is quite common in administration. If you are a vice principal, you get certain, you can look at certain files, you can sign certain things. Okay, if you are not vice principal, you just cannot do it. Okay, this is basically role-based access. Okay, so there's also something called attribute-based access control. The rights are based on attributes. For example, somebody might say the person who has let us say who has in a bank, for example, they might say that if you have more than certain amount of money banked with them, they get certain rights. It's an attribute. You have more than, you deposited more than 5 lakh rupees, you become a privileged customer and you get. So it's basically based on attributes. It's not based on user ID, it's not based on roles, etc. It's based purely on some attributes. It can be any complex attribute. Okay. Or for example, you might say, instructor can say, the guy who has scored consistently, let us say, S grade, okay, can take off without informing you. Whereas a guy who has having problems with the course, if he has to take a leave, he has to check with me before. Okay, that also is possible. Okay, things of that kind. You basically have, you get rights based on attributes. Okay, that also is possible. Okay, so it turns out most file systems use DAC, and if you go beyond DAC, you become information. You're talking about information systems. Larger and larger data is aggregated, and you start having larger systems in place. Okay, typically it is oftentimes role-based access control and sometimes MAC. Okay, MAC is tough to implement because it requires that there is a check in spite of wherever the information is flowing. Somebody is checking it all the time, and typically it's used in military guys. Military guys use it a lot. Okay, the military guys worry about what happens. For example, somebody has a switch to detonate a bomb, right? Even if you assign the privilege to somebody else, okay, you want to make sure that guy doesn't give it to somebody else, right? These are all very delicate things. You want to keep complete control of what happens. Okay? So typically MAC is for highly organized systems where there's something very critical and where you cannot trust everybody. Okay, there is a very great danger can happen if you allow discretionary access to things. Okay, this kind of thing. So most file systems are in the DAC model. there are some file systems can give you MAC, and with Linux, with SE Linux, you can get MAC. Okay, and role-based access control, it's already with Unix a bit, Linux a bit, because you have this notion of groups. Okay, and attribute-based control is not that common. It's available usually at much higher levels of abstraction. Okay, the other systems like Mac and FreeBSD and a few other things, they use also called ACLs, access control lists, where it's not based only strictly on user or group or everybody else. You can actually have much finer grained, saying that for this particular file I want to allow this person, that person, that person, or something else, this person, that person. I can specify exactly who should see what or write what, etc. There are this access ACL models give you a lot more granular way of specifying these things. So some file systems provide those kind of things. Okay. So SE Linux is one model in Linux. I'll briefly mention what all it can do. It's a fairly complex topic, so I just mentioned a few things. Okay. So it has got essentially mandatory access control MAC. It also has got similar to access control integrity controls. Who can write what? Who can modify what? Okay, and this is going to be transitive. I give it to some permission to somebody. Even if I given a write permission, if he gives it to somebody else, I still want to know whether the other party also can write. Okay, I will check it. I will not let the person I may give, the person to whom I gave it, he doesn't have the complete control over it. Okay, so basically, it also has this role-based access control (RBAC) and type enforcement architecture. Basically, there are you can have what is called a domain, and in a particular domain only certain things are possible. It's something like a type system. In a type system, for example, if it is a float, let's say it is a list, for example, right? You allow only certain operations. Let us say you have an abstract data type, and you say that I can add an element, remove an element, right? Create a list, right? Delete the complete list, or some such thing. I will not allow arbitrary manipulation, because there is a certain semantic property of a list, and if I allow arbitrary operations, it might break the semantics of the list, right? So only certain interfaces I provide. That's basically an abstract data type, and essentially what they want to do is they want to do something similar to that. They want to have a type enforcement architecture, so that only certain types of operations are allowed. Okay, just like an abstract data type. Okay, so what does SE Linux have? It has got a role, a username, and a domain. Role will basically essentially give you RBAC. Username, of course, it has to do it for mandatory access control, etc. And a domain, basically it tells you what kind of operations you can execute. Okay, so a user, for example, or a role might have multiple domains, 3 domains. Okay, and he can, whatever those domains allow him to do, he can do, not anything else. Okay, so for example, there are policy rules that you have to specify, which domains user must possess to perform certain actions with given target. Okay, it could be read, execute, write, etc. Okay, again, these things are done at the file system level. So basically, the way this SE Linux works is, you have a regular file system, and you have certain additional capabilities and functions by which you can label the files. For example, you might say that a particular domain can access /bin, or certain program can access certain daemon, for example, can access /var/log something. Okay, so you basically say, you specify in your policy rules, okay, which domain can access what, where. Okay, so and it is going to be checked every single time. Okay, if it is going to be not satisfied, then it will be, the access will not be allowed. Okay, so essentially you give policy rules, you also specify an overall policy which tells you how to label the file. Okay, a rule file and interface file that defines the domain transition. Okay, so let's just look at the domain transition. Okay, for example, on fork and exec, right? If you are familiar with Unix fork and exec, right? Basically, what happens? I can fork a program with the different permissions than what I started with, right? The child can inherit certain privileges which are the same as the parent, but in certain interesting cases in Secuirity programs, right, it turns out that you can have higher privileges also. Okay. Basically, there are some special programs which only a root or somebody will install in a particular place, and if you execute it, you get privilege escalation. Okay, you get higher privileges, right. So basically, so when you do a domain, when you do a fork, for example, you start with a particular domain and you create a new domain, right. The question is, what domain transitions are legitimate? Okay, you have to specify those things also. Okay, so if you specify those transitions, then it will be checked at runtime whether your new domains that you have created or the new essentially daemons, for example. Okay, oftentimes you are creating new daemons. Okay, so want to check if the new daemons have this what has been permitted. Okay, you check those things, only if they are permitted then you are allowed, otherwise you said no. Okay, so essentially what you can do is with this kind of policies you can ensure that I made a mistake here, I think it is DAEMON. Okay, a daemon can only be allowed to do safe actions. What are the kind of daemons I am talking about? For example, you can be HTTPD is a good example. You are running a HTTP daemon and you want to ensure that it does not go and look at my files and send it somewhere else. Okay, so you can confine it to a particular place and therefore it can avoid certain risky actions. Okay, the basic problem with the CLNX is that it is very detailed. You have to specify everything. If there is a particular program, if it happens to write to /temp, you have to give it a permission to write to /temp also. Okay, you have to give every single possible thing it needs to get its job done. Okay, so normally in our day-to-day life, we take certain things for granted, right? We can do certain things. You don't have to specify everything. But in CLNX, whether you can walk on the street, whether you can go on that street or go this street, or you can take a metro, everything has to be specified. Every single thing has to be specified. Okay, if you miss one of them, then you can't take the metros on some particular occasion. Okay, it just doesn't work. Okay, so that kind of problem is there in CLNX. That's the reason why most people do what they do is they have what is called a very permissive mode. Okay, what does it mean? You just say that by definition you give you more privileges than necessary. Okay, and then once you make sure that it's sort of working, you try to tighten the rules. Okay, but there's a problem with this. You can either over tighten it or you are still running the program at a time when too many permissive rules are available. Okay, so this is a very hard problem. The reason why it's a hard problem is because this if you take a program, whether it goes to a particular place or not is what is called undecidable problem, right? It is equivalent to halting problem, right? Because if I say that it goes to a particular place, right, that means that the intervening code will not stop, will not halt, right? If I am saying that it goes to a particular place, okay, that means that I am able to say that this particular piece of code does not halt, and you know that from theory that the halting problem is unsolvable. Okay, that means that if you give me a program, statically I cannot figure out what all the minimum amount of permission it needs. It may be that when I am branching in a particular direction, it requires certain kind of permissions. When it is branching in some other direction, it requires some other set of permissions. Okay, and if I give permissions for all the paths, then it is essentially what's happening is I am being extremely permissive. Okay, I am giving everything that has to be that it in principle to ever touch. Right, it's too permissive. Okay, because so it turns out that it is very difficult to give it the right set of permissions, and so this is a typical problem in any large system. Okay, the CLNX is not unusual in this; it is quite common in almost all systems. Another problem with the CLNX is that it is different systems may or may not support a CLNX, may or may not support the same kind of model. Now, how do you do it across? Because finally, when you are talking about a large storage system, there might be a lot of servers and there might be a lot of clients. Each may or may not have the same model. So this is a bit of a problem. Okay, so I'm just giving you some hint about the kind of problems that are there. We have not really looked at it when storage is realized through multiple nodes, multiple and distributed level, which will be starting to talk soon. So there are a lot of protocols also involved in this. So when for example, suppose I want to ensure that there are at least 3 copies of a particular file, right, in spite of failures, then there has to be a protocol between various entities in the system so that at least 3 copies are there, and this protocol will actually go over the network links and you have to ensure that somehow these links are safe from sabotage, okay, safe from, let us say, malicious tampering, etc. Okay. So the protocols have to also be secure, and so there are many things that have to be worked out so that all these things work together, which is slightly non-trivial, and so it is a very complex problem. It turns out some attempts have been made. We will talk a bit about it later. There's something called ISCSI, for example. Basically, using IPsec kind of model, you can essentially access storage devices across the internet, and basically you will be protected through the IPsec, whatever IPsec does for IPv6 or even IPv4. The same thing can be used as a way to protect yourself. So these are some of the things that also you can do. Okay. So I think I just wanted to give a flavor of the kind of problems that are there in security for storage systems. So it's a fairly intricate problem because there are many attack vectors. As you saw it in the case of Blu-ray, there was in the case of CSS for DVDs, the encryption mechanism was broken, so they figured out a way to crack it. In the case of Blu-ray, that was fixed a bit properly, so that route they didn't take. They decided to go and see what is there in memory. Okay, so this is a problem with any system which is trying to give you the device in your hands, because finally you can do what you want to do with the device once you bought it. Okay, so you can essentially use some brute force or other clever techniques by which you can look into it and get out the secrets. Okay, so and basically what's happening is that cryptographic mechanisms have been widely used and they are reasonably good. Mathematicians and people have worked on it quite a bit. Now crypto techniques are quite good. The real problem is, because they are so good, nobody who wants to crack a system will try to crack the cryptography. They will crack the more easier parts of it. So nowadays cryptography is no longer an important issue for most people, because assume that nobody is trying to crack it through that route. Once upon a time, when cryptography was a bit weak, people were saying, okay, I will figure out a way of cracking cryptography and get an answer out. But now with AES and other kinds of cryptographic routines, it's extremely difficult to crack cryptography. So the standard technique is to not work on the cryptographic level. If somebody is doing cryptography, they'll say, I will not touch that part, I will go and crack it outside of the cryptographic domain. I'll figure out a way to do it. Okay. So again, for doing that, you need system-wide analysis. Again, storage systems are the same system, same problem. You could be having problems at the network level, at the device level, at the protocol level. You have to have a comprehensive model for all these things. Then you probably find maybe you might find some attack ways to both strengthen the system or crack the system. Okay. You have to do all of it, otherwise it's not possible. Okay, I think I just wanted to give a flavor of what is security for storage systems. I think we will stop here today and probably continue with another short lecture on reliability as another thing that storage systems have to worry about.